Now we have the second derivative test, or really we should call it the second order derivative test. Now, since we have three possible outcomes, the three-dimensional second order derivative test is different from the two-dimensional test. This one uses a formula first. So let's suppose we have found the critical point AB. We are going to find this value, we'll call it D of AB, by taking the second order partial derivative with respect to x and x of AB times the second order partial derivative with respect to y and y of the value AB minus the second order partial derivative of x and y. And remember, the order really there doesn't matter, but you got to do one and then the other. And then plugging in the value of AB and then squaring that value. So keep in mind, all of these are numbers. We're going to plug in A of our critical point in for x and B in for y. So we're going to get a numerical value. We can either use the second order derivative of x and x or the second order derivative of y and y for the test, but we're going to use x and x in our notes. So first of all, if this value is greater than 0, in other words, if it is positive, then we are either going to have a relative max or min. If that second partial derivative is positive, guess what we're going to have? We're actually going to have a relative min. If the second order is negative, we're going to have a relative max. I know that may seem counterintuitive, but let's go back to our second derivatives in one variable. If a second derivative is positive, that means we have a concave up, which will give us a minimum. If our second derivative is negative, it means it's concave down, which will give us a maximum. Now, if our D value is negative, that means we're going to have a saddle point. If it equals 0, we have no idea. It's inconclusive. So let's keep that handy and take a look at example B. We're going to use the function and critical points found in example A and locate any relative extrema. Rewriting that equation, we have f of xy equals x squared plus y squared minus xy minus 3y plus 5. And if you recall, our first derivative with respect to x was 2x minus y. Our first derivative with respect to y was 2y minus x minus 3. And our critical value was the point 1, 2. So now we need to find the second order partial derivative both with respect to x. So looking at the f of x over here, the derivative with x again would be 2. Second order partial derivative of y and then y, if we take that derivative again with y, would be 2. And with xy, it would be a negative 1. So now we have to find our D. So remember, we take the 2 times the 2 minus that negative 1 squared, and we get a D value of 4 minus 1, which is 3, which is greater than 0. So based on our table, we have found out that D is positive, and our second order partial derivative of x and x is also positive. It was a positive 2. Positive and positive means we have a relative min. But remember, we're in 3 dimensions. We have found the 2 input values of 1 and 2. So now we need to plug it back in to our original equation and find our output value. So f of 1 and 2 will equal a 1 squared plus 2 squared minus 1 times 2 minus 3 times 2 plus 5. See if I can squeeze all of that in there. And if I've done all of that correctly, that equals the number 2. So we have a relative min occurs at the point 1, 2, and 2.